I'm going to try problem number 5 out of the Module 4 homework to run the basic framework of the hypothesis as well as take a look at the p-value. Of course, this is asking if there's enough evidence to declare a significantly higher portion of women than men believe weight is a factor in purchasing a laptop. So there's no mention of the equal sign in there, so I'm going to use greater than as my HA, and in this case it's the population of women greater than the population of men. So again, the opposite converse is true up here. Population of women, population of men. Now, it looks like you can restate that as the population of women minus population of men is less than or equal to 0 and not, greater than 0. I believe they say the same thing, but just put both for the answer. Now I'm going to draw my distribution. There it is, and I have my arrow up here, rejection area over here. There's the median. And what's next? The next thing I need to do is figure out what this line is, my critical value. So how do I do that? In this case, we have a large enough population, we're going to use a z-value. So this is going to be a critical z, and we can run that with our off the chart if you want, because we know our significance level is 0.08. So you can just go to the z table, grab that, do that real quick. I'm going to come down here. I highlighted some of the key ones, but 8% is not one that I highlighted. There's 6. Working our way, there's 7. 8% looks like it's right around 1.40. I can also run the norms inverse function on Excel for 0.08, and it's actually going to spit out, and it shows on here negative 1.40. But again, because we've drawn ourselves out, we know this is going to be a positive number. The z-table doesn't know whether I'm a right or left side here. So my critical z is 1.40. Again, see how my framework of knowing what I'm doing on the chart takes some of these negatives and confusing numbers and defines them for me and gets me on track. That's what's important. Now, next thing we want is our test statistic. Again, not getting into that here. Run the math, punch your numbers, show your work. But the result, 2.649. 2.649. And I have my critical as 1.40. So in this case, guess what? That puts us way inside the rejection area. So in this case, in this example, we are going to be rejecting the null hypothesis. Okay, so that's straightforward. We're greater than, our test statistic is greater than our critical value. Inside the rejection zone, we reject it. Now, that's easy, kind of. P-value. We can either back it into the chart, but let's use the norms dist for that. And what are we going to put in there? We're going to put in our critical value. No, we're going to put in our test statistic. Almost got you. Test statistic goes in here. So we're interested in this because this is essentially, and this is the little bit I understand about p-value, this is defining what our rejection zone could be. What it could be if we wanted a valid test. Okay, so let's put in norms dist 2.649. Okay, so I've got that, and the problem shows me that spits out 0.996. Now, don't look at that 0.996 yet. Let's just look at this and say, what do we expect out of our p-value? Do we expect something very small? Or do we expect something very large? And one of the things, the definitions I found of p-value is it's the area of that rejection area here. So really, we're defining this area right here. Hey, it's small. We expect a small number. Well, I punch my numbers into Excel, and what do I get? I get a big percentage, 99%. Guess what? That tells me Excel is spitting out this whole area and not this one. So what do I have to do? 1 minus 0.996 equals 0.004. That, my friends, is the p-value. So again, thinking about what we want to accomplish. Now, if this test statistic was negative 2.6, guess what? I'd be expecting a huge number for my p-value because it's all, let's see what that would look like. If I draw that here, if this was my test stat, I would be expecting all this area to be encompassed by my p-value. In that case, we'd actually be looking, if you change this to negative, we'd actually be looking at 99.6% of the distribution is in this area. So I hope that this whole 1 minus thing really had me stumped. I don't completely understand it, so take this information at your own risk. But I think if we know what to expect going into it, what that number should look like, if you need to 1 minus it, then 1 minus it to get it into where you need it to be.